In this problem, we need to find these expected values for the stationary states xi0 and xi1. So for this video, I'm going to focus on finding these three terms over here for xi0. So to start off, let us remind ourselves what the expression for xi0 is. So xi0 is equal to all these constants multiplied by e to the power of negative m omega divided by 2hx squared. And then to save ourselves some time, I'm going to let this one big giant constant over here be equal to alpha. So this could save us a lot of time instead of writing out all these constants over here. And then I'm also going to do a substitution. M omega divided by h bar x, I'm going to let this be equal to y. And by doing the substitution, I can simplify the exponent as being equal to e to the power of negative y squared divided by 2. So this is just for time saving. So first of all, we need to find the expected value of x. And recall that the formula for the expected value is that you take the wave function, you take the conjugate, and then you multiply it by x, because we're looking for the expected value of x, and then we multiply it by the wave function, and then we integrate it. So immediately, first of all, you should notice that for this wave function here, there is this time component, and it's equal to e to the power of negative I ent divided by h bar. So this is, once again, this is proven earlier in the book. This is the time component. And then you see that once you've taken the conjugate, this negative sign becomes a positive. And then over here in this component over here, you also have this time component. But then without the conjugate, you still retain this negative sign. So in the end, both of these just cancel out. So in the end, this whole expression over here, we can actually just ignore the t component entirely, and then write our formula as x multiplied by the zero stationary state square dx. So in this case, so you can see that we can go from this formula, which is the definition of expected value of x, to this expression here, which we can very easily calculate because we know what xi0 is. We just multiply by x and then we can integrate it. So notice that this is actually an odd function. So this is kind of similar to what we had in the previous question. So if you check out question 2.10c, you see that we also had to deal with that odd function. And then if you integrate an odd function from negative a all the way to positive a, so it's a symmetric, so you can review it like this. You integrate from negative a all the way to positive a, and this is and if this is an odd function, and they integrate it from negative a to positive a, then this is going to be equal to 0. So I've also proven this result in the previous video in 2.10c, so you can check that out if you're interested. Because we know that this expression here is an odd function, that's why this whole integral is equal to 0. So essentially we've already found what the expected value of x is at 0, and which should make sense because the potential of the quantum harmonic oscillator is symmetrical. And moving on to the expected value of p, this can be calculated by taking the time derivative of the expected value of x, and since this expression is equal to 0, then of course this is also going to be equal to 0. So we found this as well. This is also equal to 0. So now the remaining challenge is to find the expected value of x squared. Now this is going to be less direct than these two results because it's not going to be equal to 0. So now we will have to apply this formula over here. So by the same reasoning, we can bypass having to apply the Schrödinger equation with the t component because in the end they just cancel out. So the formula for the expected value of x squared is just equal to x squared multiplied by xi0 squared dx. So you see it's very similar to what we have over here, but this time instead of an x, we have x squared. And we know what xi0 is, so we can just substitute this right in. So we have alpha squared. So you see now why I use alpha, so I can save a lot of time writing these constants out. And then for this e component, I have x squared times e to the power of negative y squared dx. Now this is in terms of y, this is in terms of x, so I'm going to change everything to become in terms of y. So recall the earlier substitution that we did. So we're going to do the substitution for this integral as well. So you see that m omega divided by h bar dx is equal to dy. So that means dx is equal to all these constants over here times dy. So we're going to have alpha squared, negative infinity to infinity, x squared, that's going to be equal to, so x, you see that it's equal to the square root of h bar divided by m omega times y. So x squared is just going to be equal to h bar divided by m omega times y squared. And then here we can just retain this term, e to the power of negative y squared. And then dx is equal to the square root of h bar divided by m omega dy. So moving on. So I'm going to pull out the constants first. So we have these two pretty much identical terms except for the square root. So we can group them up together. 3 over 2. And then we have this integral from negative infinity to infinity, y squared e to the power of negative y squared dy. So the way you evaluate this integral over here, so once again in the previous video 2.10c, I've also I've also given a demonstration in this video on how to evaluate this integral. And then I'm not going to repeat my efforts from that video, so if you're interested, you can check out that last video over there to see how you can deal with this integral. So basically you just use integration by parts. You break up the integral into these two components. But then after you do the, if you do the integration by parts, you see that this integral over here is equal to 1/2 times the Gaussian integral. And this integral over here is equal to the square root of pi. So you can use a double integral to prove this. This is a rather famous result. So I'm not going to prove this here. So using the result from the last video, we know that this integral over here is equal to this integral, and then we know that this integral is equal to the square root of pi. So this whole expression is equal to the square root of pi divided by 2. So you can check out the proof of why this is the case in the last video, 2.10c. So now applying this result directly, so all we have to do now is just to handle a few constants. So we have h bar divided by m omega 3 over 2. We have the square root of pi divided by 2. And then alpha squared, I'm going to put back the constants in, that's just equal to m omega divided by pi h bar square root. So originally it was 1/4, now we square it, so it's now a square root. So now we can simplify some of these terms. So this pi, they cancel out, and you see that some of these terms can cancel out as well. So again, pull out a square root from this term over here. And then after I do that, all I'm left with is h bar divided by m omega. All these conveniently cancel out. So in the end, we're left with h bar divided by 2m omega. And this is the answer. So this will be the expected value of x squared. So in this video, we found the expected value of x squared, and we found the expected value of momentum, which is 0, and the expected value of x, which is also 0.